Hi, good afternoon. This is the FGF User Group virtual meeting. Our speaker today is Adam Day. For your information, we are Re3D. My name is Michael Prigil. We host this virtual meeting for the benefit of the whole community, all FGF enthusiasts. You don't have to be a Re3D FGF printer user to join, participate, or share knowledge in this space. As noted, we will be hearing from our speaker today and recording. You are being recorded right now. At the end of Adam's talk, we will turn off the recording and have Q&A, or we'll have Q&A, and then we will stop recording and we can continue conversation off the record, as it were. I have put my email in the group chat. If you are an FGF user, enthusiast, interested in giving a future version of this talk, please do get in touch with me. We're meeting monthly. Our speaker is Adam Day. He is a senior research and design engineer at the Autodesk Technology Center in Boston. According to his online biography, which I'm going to share with you, he's already laughing. Adam has a very interesting background. He has a background in landscape architecture and experience in environmental design, metal fabrication, and firefighting. He's mentored students in project planning and delivery as a gateway project mentor at Boston Architectural College. Very cool. Additionally, he's worked in landscape design, environmental design, and firefighting roles for various organizations such as John Brooks Landscapes, Native Landscapes, the National Park Service, and the Bureau of Land Management. And he has a BSLA in landscape architecture from Colorado State University. Colorful background, really interesting. Maybe we talk more about your diverse skill set later, Adam. Anyway, his talk will be on the challenges of printing a 5-meter pedestrian bridge. With that, I'll let Adam take over, and thank you so much for attending.
Awesome. Thank you so much, Michael. So my background, I'll just give a short connection. Started out in landscape architecture, worked for a variety of agencies doing a whole bunch of different things. Ended up at some point in my career working for a playground equipment company, doing a lot of mechanical design for playground equipment and redesigns for US safety standards, and as well as doing layouts. And then at that point, we were 3D printing all of our prototypes. And so that's really why I got into 3D printing. And that was, I don't know, 15 years ago, maybe longer. And so we were doing, at the time, it became a nice tool for doing all of the prototyping for all of our safety stuff. And so just kind of went from there, moved from that world kind of into more mechanical engineering and design and into Autodesk. So the project today I'm going to be talking about is the Autodesk DAR Smart Bridge. So this is a project we did in the Technology Center here in Boston, actually right out the window here. And it is a 5-meter pedestrian bridge. So let me move to the next slide. There we go. So this is a picture of the finished bridge at Autodesk University. And so this bridge was So this is actually Peter Story, who's the project manager on the bridge. The Technology Center here is a unique space where we get to do a wide variety of projects with a ton of different collaborators, including internal research teams. Peter is an Autodesk research engineer also. I am one of the shop staff here at the Technology Center, so we're the subject matter experts for each of these specific fields, and I'm the additive subject matter expert. Stephanie Pender, we played a huge role in this. She's the robotics subject matter expert here in Boston. So we like to tell the story of how we come about this. A sketch is a nice way to kind of show what we're learning and the pathway we're trying to go. Initially, they came in there. The goal was to create a bridge on site. So how are we going to 3D print a bridge on a construction site? And so we went kind of farther back and said, okay, what is the process we're going to do? We're going to, learning and our data analysis feeds into our constraints. So our client-driven, adaptable, what are the codes and standards, into the material supplier, resiliency, local materials. How do we grow this project Is it scalable? Is this idea adaptable so it could be done in other places? And then what is the feeling like? What is it like to use a bridge like this? Do people enjoy it? So, yeah, research we needed to conduct to get this bridge done. One was toolpaths for structural performance, geometric freedom. So how are we going to actually print it? What are the toolpath processes? How can we create toolpaths so we can print something this large? And then also, how do we do some interesting design? In this case, what we call process-informed generative design. So generative design being one of our AI design tools. We give it a bunch of constraints and the material information, and then this tool basically creates the shape for us, growing and subtracting material as needed through hundreds and thousands of iterations. So to do that, we need material characterization. So the system needs to know all of the information about those materials, the strength in all the directions. And then we also wanted to conduct some research on sensors. So how are we going to get that process information that we can use for the generative design? So when we initiated this project, most of the examples of these large polymer printing were continuous tool paths without any pauses, and which is great. And actually, we use that for 3D CP here in Boston. But there's a limit to the complexity you can do. You can't have these floating islands. Everything has to be able to be connected. So we wanted to see if we could try to do discontinuous, which is what you'd find on your normal FFF printer, or if you're having a re3D terabaud or gigabot or something like that, which we have upstairs. Right, so here's our layer deposition. With our traditional slicing, obviously on a small scale, issues like this are not a problem because of the way you can do pressure advance and the way and how little material is coming out in nozzle size. But when you get to those larger sizes, you start to have these really big issues. So then we started doing something we do in our subtractive processes, lead in and lead outs. So starting our tool moves in the earlies, but the problem is they leave these gnarly scars on the edge. And then with some extra, we were able to take all of our lead in, lead out motions and align them to our toolpaths. So follow the perimeter shape, and then we can kind of like extruder on and off a little bit early and late. Because obviously these bead widths, these are like 18 millimeter bead width, pretty big. We're flowing about 20 pounds an hour of polymer into this print. So these photos, you can see the final quality of the print. We were able to get really good exterior surfaces. You can see some of the joints kind of on the lower right picture. And then you can see on the infill section where we're starting and stopping those tool paths. So to make sure that we have all of our defects in the internal area where no one's going to see it. So the next thing is our angled printing. So we want to print this bridge. It's 5 meters long. We're using a ton of polymer, bonded very strongly. We do not want to do any support structures, but how do we print something like this? So we took cues from a bunch of things we had seen over the years. A bunch of those no support. So we actually started the print at 45 degrees. Here is our first test of that part. So that our overhang angle, essentially we have a vertical overhang angle. Normally you're out at 45. When we tilt the whole build plate, that gives us an overhang angle, so we can do the entire structure without any supports. With that context, we can talk about our design to manufacturing workflow. In this particular case, typically we would do concept design. That becomes then go through design development, then start to perform structural analysis before moving to the steps needed to produce it. So manufacturing, detailing, toolpath generation, and machine simulation. So by doing process-informed design, we start to take some of the toolpath generation and machine limits and load them into the actual shape design, so that we're trying to, I mean, and all engineers kind of do this sort of intuitively, but because we're using a generative design tool to give us the shape, we need to do this in a more intentional way. when you're doing DFAM, you do additive DFAM, you just kind of like, the limits. So when you create the shapes, but we had to do this in a very specific way because we're using an AI system to generate the shape. So concept design. So in this case, thinking about how we were going to actually like get the bridge. So this shows us the image one, we're seeing we need a deck to walk on, right? This is a bridge, and we need people to be able to use it. We need a build plate to print on and the design domain, kind of the area that we could possibly print. This gives us kind of limited space to produce the support underneath the deck. So if by extending the build plate up, that gives us a larger design domain, more area that we can build the support structures. And we kind of like move it into the print area. And then in 3, you can kind of see, where is our final design domain. So this is the area that we have to restrict the AI software into putting geometry. So we're saying, okay, we can't allow it to build in that area. And then this is our process-informed generative design, right? You can see our robot track. You can see the bounding limits of our machine, our robot, the minimum thickness of our beads, or the minimum thickness of our element, in this case, 2 beads, our maximum overhang angle of 45, and then our print direction. So those are our constraints. And then the load cases, and that's what we kind of tell the AI system what we're doing. This is a little video of the generative design software running. So this is the iterations it's creating. So how it's going from the initial shape and then removing material and then finding that areas are too weak and then adding material until our final study. So you can see a stress reference, high being red, blue being low. So we're able to get a pretty thinned out structure with very low stress, which is kind of cool. And then, of course, a little bit of manual editing for things that we know or, remove particularly difficult members, things like that. And then infill. So for this, we're going to use a gyroid infill for this bridge, which is a pretty typical infill pattern. We do need to do... So initially we did like a simulation of using a volumetric lattice infill, but then it turns out that the gyroid infill that we had chosen when we ran simulations on it, like your typical FFF style gyroid infill, worked great and provided plenty of stiffness. So it was an easy choice. So now we can move our story to the kind of the final part. We can look at the fabrication steps, which is probably what you're all interested in. A little about the technology centers. There are a variety of them around the world. San Francisco, Toronto, Boston, where I am, and then Birmingham, UK. And so this project was primarily started in the Birmingham, UK office, finished here in Boston. So this is a picture of the build plate. So a few things. We had the... Obviously, larger the print, the more polymer volume you put out, warping and cracking are a bigger issue. Right? A little bit of glue on a regular, nice textured PEI build plate, those will get you pretty well on your normal size prints. When you start to move up to something this big, you have adhesion issues. So we took some kind of notes from some other things we had seen. So what we have here is an aluminum plate anchored to a structure at 45 degrees. You can see when we craned it into place. We have also pellets that are adhered to this build plate in the shape of the first kind of layers. And then as we were going, and the solid aluminum build plate has some structure on the back to keep the build plate itself from warping. And then once we got to about 100 layers, we'd also designed in a support structure. So you can see in white with the bolts going through it, an aluminum clamping plate. And so once we had started the print, we were able to clamp the piece to the build plate for the rest of the build. It was quite heavy, and when you're 5 meters out from your build plate, you have a ton of force pulling down on this. And you can see this build plate is anchored to the floor. And then here is the full print video. So this was 200 hours, although we had to do it over a few weeks because our EH&S teams wouldn't let us run 24/7. So the system here, the robot, the dry air feeding system, that can all run 24/7. The issue for us was just staffing and safety concerns. We're a software company, and sometimes it's easy to forget that. So we have different risk tolerance than, say, your typical manufacturing company. So the final weight of this bridge was 960 kilograms. The layer height was 3 millimeters, and we covered over 24 kilometers of tool path. So a pretty long tool path. You can also see in this video heat lamps. So one of the issues we had, and we'll get to it at some point, was layer temperature. So that was one of the ways we were able to remedy this. And then this is the final result of the bridge in place. So this bridge was actually sensorized so that as you walk on it, you can see the live load. So we have a digital twin of the bridge. There are environmental and temperature sensors all along it. You can see the strain data showing on the bridge itself, which I thought was awesome. This is Kian, who's in charge of the sensor project, having some fun, being really excited. Yeah, and so some conclusions, right? So we're designing for anisotropy. Obviously, you can see here how much stronger, yeah, and everyone knows this, how much stronger your prints are in X and Y than they are in up and Z, just because of laser adhesion. And so this is a big deal when we're trying to print a bridge. We also know that so we use this approximation of the gyro to infill for our structural simulation. I'll move on to, sorry, I missed that section. But this is what we printed. So this was this kind of an issue of like, we couldn't run an FEA on the exact infill pattern that we wanted to. And so we had to create an approximation and then do the FEA. And then the big issue that we ran into was stabilization of layer temperature. So we, on this print, had included some infrared temperature sensing system at the edge of the extruder. So we're running 3 heat bands. The pellets are running through a dry air system coming to the top, getting pushed through the screw. And then we're watching the temperature as it's coming out of the nozzle, so as the layers are being deposited, and then the temperature previous, so of the layer that's getting covered over, because there's a narrow range of temperatures that you want to stay in to get good layer adhesion, and we were worried that we might be getting too hot, and that we would need to slow the robot down, and so we wrote a script so that the robot would slow down if the layer temperature difference was too high. Turned out that because we're only flowing 20 pounds an hour, and because the structure is so big, we really needed to be flowing a lot more material. So our layer temperatures were generally right at the edge of where we wanted them to be, or a little under sometimes. So we took a bunch of infrared heat lamps, the same ones you use for curing like paint on cars and things like that. And we attached them to the cell and on the robot track and around there so that we could stabilize that layer temperature to kind of reduce the warping and keep us in the range that would produce good layer bonds. Yeah, so this is the finished bridge. And so thank you for sitting through. This presentation was also adapted from something we gave before, but I think this was a really fun project. It was really interesting to see. You can actually see in blue, we used the boat stands. So, they're kind of large steel stands with a screw, so you can adjust the height, and they have a big bearing surface, like a ball socket, and then a flat plate. So we can put them up in the bridge as we print it along to help carry that 960 kilogram load across the whole cell. Man. And so a few other things to note. So we did this bridge. So previous to doing the 5-meter bridge, we actually did a 2-meter bridge. This one we did in Birmingham, and on a different extrusion system, a much smaller extrusion system. But it was this kind of is where we were able to do a lot of the iterations, get a lot of the ideas. That's where we started to see problems with doing the build plate flat. And when we decided, okay, maybe we'll do some overhangs. Also, the part of like if you're going to do a print like this on a construction site, you have to start on one side and finish on the other. Like crossing the gap of the whole thing all of the time creates a lot of pauses, a lot of time for it to cool. So you can see the difference in design from the 2 meter bridge to the 5 meter bridge. And then of course there's some of our CEO and stuff on the bridge at the conference, and they did such a good job of dressing it up. Although we did have to add handrails, turns out. So you can see the handrails we made for it. Yeah, and then a few kind of little bonus things. Um, this is kind of the generative design of the 2 meter bridge, showing this is how those algorithms run. It's just kind of, I think, really fun to see. And we're able to do like, what is our max overhang angle? What is the orientation of the part we want to print? What is the minimum element thickness? So like, what is the smallest, little string of material it can put out? So which is really helpful for having to do it. The sensors that we put in there, so these are they're fiber brag grading sensors. So they're basically like glass fiber fiber optic cable sensors. So these were also on the 2 meter bridge. They shine light down the sensor, and then the gratings in there reflect certain wavelengths, and so you can see how it is moved by the wavelength and how it's reflected when you get the end. So as you can see, the reflected wavelength gives you an idea of the strain. So we put a ton of these through the bridge. You can see on the 2 meter bridge where they were placed. And then you can actually see these guys putting them in. On the 5 meter bridge, we actually used the little hand router that we attached to the robot to mill some channels. And then we could put in the fiber optic strain gauges and then use the extruder to come back and fill in those channels we had cut after those strain gauges were placed. So it really was a hybrid setup instead of just a purely additive setup. That was James and Peter putting them in Birmingham. Here's our slicing. So we did this whole thing in Fusion 360, which is pretty wild. The design, the slicing, all of that stuff, even the robot control. So, and you can see our 45-degree oriented build slicing. And then you can see the sensor locations, strange gauge rosettes that we used. And then that's also where the environmental sensors were. And then this is routing all of the sensors. So you can see as we're printing, there are certain times as we're printing where we need to like run cabling, even though it's still being printed. Otherwise, we'll lose access to those areas. So you can see all of the cables getting stuffed in the bridge. And you can see on the top, starting on the, I guess it's my left, you can see printing. And then as the printing paused, you can see machining happening. And then you can see the pockets. And then you can see us weaving cables through. So, and these are all the cables running through the bridge. Nicely tucked away. I know at first it was such a mess. And then finally, once we got it all cleaned up, it looked really nice. And then temperature data. So this is temperature data from the initial 2 meter print. So you can see here we're getting below temp on a lot of these, the bottom section where you're traversing a ton of area, right? You're printing over here, moving long distances, printing some more, moving. You have a lot of surface area, a lot of like surface area to print. And then coming up to the top sections, we're kind of getting into optimal temperature range. Even on the 2 meter bridge, this also was part of why we found it so important to slice at 45, print with no supports, getting more consistent layer times, or as opposed to having some really long ones at the bottom and really short ones at the top. Right, here's our interlayer temperature and how it affects tensile strength in the Z direction. Just kind of an overview of that. Interlayer temperature is super important, and you never think about it in the small scale FFF because it's very easy to control, and there's so much less thermal mass that's really easy to reheat the layer when you come around with the next one. Whereas in the large scale with FGF, with these larger extruders, it's a lot more important. So yeah. And of course, we talk about design to make, trying to do it all in one platform. So we're doing our design, we're doing our optimization, we're doing our simulation, we're doing everything in one piece. And we were able to do our robot simulation. Although I think this is still a preview feature. So if you want to do robot control, we have an insider program for Fusion. Yeah. Last couple slides, critical components. So we did a couple of these prints a number of times before we printed the actual full size bridge. So you can see on the far left, us printing the initial like first layer kind of joinery, can we make these jumps? What does it look like? This is also where we did a lot of the fine tuning of that start and stop, so that we could get those clean, crisp start and stops. And then you can see in the center section, this was kind of our most difficult overhang. So where we are kind of most concerned about supports. And then the transition in the end to that final sections sitting out, worrying about kind of the parts sagging or layers not adhering well. So, yeah. And then this is the final scan. So this is a comparison of the geometric accuracy from the print. So we scanned the print after we did the full bridge, and then compared it to the design model. And it was really accurate. I was super impressed. I thought we were going to get a ton of distortion by the end, especially with all the shrinkage. But we were able to keep it really close. So yeah, we used a Faro Focus laser scanner. And then, yeah, so special thanks to Peter Story for, allowing me to take all of his assets and repackage them into an awesome presentation for you all. Yeah, I probably went through that a little quicker. So if anyone has questions, I am more than happy to go back through any slides.
Oh, great. Thank you. Thank you so much, Adam. That was fantastic. And I'm sure we have numerous questions. Before we field questions, we'll continue to record for posterity. But if anybody's got questions or discussion they want to initiate off the record, I'll stop the recording in a bit and then we'll continue. So, but for now, it's still recording.
Awesome.
There are a couple of questions there's a question in the chat.
Okay, great. Oh, I see it. Yeah, so which polymers do we use to 3D print the two bridges? So the first printed bridge is a carbon fiber fill ABS, which is kind of the most common material in that large scale additive space. I mean, a super common pellet, pretty easy to get. Obviously ABS has a lot of strength and resilience. It's pretty good material, and it does have a lot of warping. The carbon fiber does a few things, fiber fill, but one of them is reduce that shrinkage, and that's kind of the biggest benefit we found for the large format additive. And then you can see the color difference in the second one. So the second one, it was recycled PETG with glass fiber. So that was all from Mitsubishi Chemical. So pretty easy to get material. That was really easy to print with. We had tried PET and fiber fill, glass fiber fill, and carbon fiber fill PET on some of the tests. Had a lot of trouble because it's a semi-crystalline. I'm pretty sure. And so running out of the optimal temperature range and then either getting it burning in the extruder or having it start to solidify, not staying in the right state. So, but yeah, the glass fiber fill PET was really nice material to work with, worked really well. A super added benefit that it's all recycled material. I think the fiber was from Chop Turbines. And then I think it was those large like 5-gallon water bottles for like your water cooler. So yeah. Oh, nice. So trials to get a successful print. Yeah. So actually, the 2-meter bridge we did a couple times because we learned a bunch of things as we were going through it. There were a couple print failures. We also had it's just an extruder failure on that. That one is a hybrid system, and so we had like a drive motor problem. on the 2 meter. The 5 meter, we just did those 3 test section prints, and then we just ran the full thing once. So we were able, that was one print, although spread out over a bunch of days, and requiring preheating in the morning. I wish we could have run it 24/7. It would have been really cool, because it was only 200 hours, but spread out over, a bunch of 12, 14-hour days. So yeah, so one single print, but with a lot of testing all of the really scary areas ahead of time. And then seeing that those are printing well and then being like, all right, we'll go for it. So yeah. And then okay. So the robot toolpath planning. Oh yeah. Robot toolpath planning is a little tricky. So there is, and actually maybe I can send it out at some point. In Fusion 360, there is a robot add-in that's part of the insider preview. Uh, and so it's like basically an app that you load into Fusion that allows you to do to simulate the robot location, and then do so we can. I'm trying to think of exactly how to explain this. Basically, we used FFF toolpath parameters, and then we were able to post-process that FFF toolpath to a robot code in Fusion. And then we were able to use this add-in that one of the research teams at Autodesk has created to do the simulation and change the lead-ins and lead-outs and do some of that stuff. So I know, so it's called the robotics add-in tech preview, and it's part of the Fusion 360 Insider, which I believe is free. But I'll have to double check on that. There's also, I think both Peter Story and Stephanie Pender have given other kind of very detailed talks, and I could be more than happy to send out information on that, and I can always connect you about the robot programming. So we've had a few people, and we're always looking for interesting companies and or university teams that want to be doing robotic programming in Fusion, because it's something that us and research think is very valuable. So we're trying to make sure that the product teams know that. So the more interested you are in being able to do that in Fusion, let us know, and we can try to get them on board. Yeah, shutdown and startup. So we do purging. Start of each day, we're coming in, heat lamps are coming on. Actually, first thing that comes on is the pellet dryer, and that's coming on at like 4 a.m. Automatically every morning, so that the pellets are fully dried. And we're using it's a dry air, 100-kilogram pellet chambers. So the dryer comes on, that stuff starts drying before everyone gets into the office. First person in turns on the heat lamps, so we're starting to preheat the previous, like, whatever 100-layer area. Then robots on, all of that. We have saved. At this point, we're also streaming code to the robot, just because of the length of code for the robot. It basically, our controller's a little on the older side. It couldn't store all of the robot code for the entire bridge in one file. So we are streaming it too. So we have it paused, and we can save that line in the code. So then we can move the robot out to a purging area, start heating up all the extruders. Once we're kind of close to temp, we'll start turning the screw, feeding and purging out old material. At that point, we have like a purge material we also buy, like purge pellets. It's the same stuff that you use for cleaning injection molding screws. They do it at the beginning and end of injection molding runs. So we just buy that. So that is already in the barrel at that point. So that's coming out. New PETG pellets are coming in from the dryer, and we'll purge that for like a couple minutes. Then that is, once we're purging well, temperatures are all checked out, then the robot will move back and resume printing. And so we're able to see the interlayer temperature range. Ideally, you wouldn't have to do that. You could run 24/7, so you wouldn't be like, oh, let me preheat the previous layers and start in the morning and do all this stuff. All of that is a huge issue that was just because we couldn't run 24/7. Staffing that was a little bit tricky for us. And then shut down. We'll get to a certain area. We're printing whatever 10 hours or something of actual runtime. Reaching the end of that, making sure it's stopping at the end, making sure it's done to infill and then a parameter, and then pausing. It's saving its location. Then we're moving the robot out to the purge location, putting in some of the purge material, the injection molds, screw cleaning pellets, purging that out, cool everything down, shut the machine off, and then start it all up again the next morning. So lots of note taking, lots of being very careful, a team of us kind of there the whole way. And we would kind of like take shifts watching it. I mean, it's running pretty much autonomously when it's running, but you know, one of us is around just to make sure we don't notice anything weird. We're also using a pneumatic vibrator up at the feed. So where the pellets are coming into the extruder screw, just because we're at kind of a weird angle. We've had to print like a custom funnel for the pellets to come down to go into the screw also. So yeah. Awesome. Yeah, it was a really cool project. I mean, it took a whole team of us, a really fun thing to do. Yeah, and we've produced, you know, a bunch of stuff about it, AU talks, things like that. So I think Stephanie even did a class on how to do the robot programming. So I bet we can find that.
Okay, are there any more questions? Okay, well, we can continue in a minute off the record, but for the sake of the recording, let me thank Adam Day very much for a really fantastic talk, really fascinating project. And we're looking forward to seeing more in the future, see where this goes. And thank you very much.